Hey everyone, I'm your host, Dr. Dean Mitchell. As my regular listeners know, this podcast hopes to bring you the best medical information anytime, anywhere. So get comfortable, get ready. You're about to enter the Smartest Doctor in the Room podcast. Now, we all rely on our healthcare news from the popular media, newspapers, TV, and now social media. The way it works is that these outlets glean from credible medical journals like the New England Journal of Medicine or the Journal of the American Medical Association, JAMA, the latest research papers, and they tend to summarize the latest headline-grabbing findings. The problem is this: even though a study was published in a very respectable journal, doesn't mean that it's true or that you should change maybe your current treatment. A key to any study is the statistical methods that are used to design the study and analyze the data. And this is not as straightforward as it seems. For example, years ago, a study came out reporting that I think decaf coffee was associated with pancreatic cancer. Or another study came out that said statins, which are used for cholesterol lowering, caused Alzheimer's dementia. When these studies hit the news, it causes a whirlwind of confusion. And then a lot of times subsequent studies don't confirm these findings. So how are we supposed to interpret new medical findings? Well, we have to turn to a branch of mathematics, probability and statistics. Now, before you turn off the podcast, we are not going to go into a math lesson here. I know that back in school, there are essentially two categories of students, the ones that are good at math and the ones that weren't. Now, I might have been in the latter type, but I do admit to enjoying statistics. Like when I was a kid growing up, I loved learning all the baseball batting averages and things like that, and memorizing my favorite players' numbers. But that's basically static statistics. Real big-time statistics, which actually is now being done by major league clubs, especially their general managers. They're looking at data to figure out what players will bring them the most wins and championships to their team. Think like the movie Moneyball. Well, the same goes for medicine. Big-time, well-funded studies rely on the power of statistics to decide whether a specific treatment is beneficial or dangerous. My guest today, Professor Chris Schmid, is the head of biostatistics at Brown University, my alma mater. And I came across an article, one of his many, that discussed even a new approach to analyzing medical data called Bayesian inference, which we'll get to later on. But I'm hoping, and my goal with today's podcast is for all of us to learn how to credibly interpret, to some degree, medical studies. So I'm really pleased to welcome Professor Chris Schmid to the podcast.
Thanks, Dean. Glad to be here, and hopefully we can illuminate more than baseball statistics, although I got to say that was how I got into this field myself.
Is that right? Okay.
Yeah.
I assume you were one of the kids that were good at math from early on, though.
I was good in math, yeah, but I always liked numbers, and numbers are something that a lot of people sort of have trouble with. But I've often found that it's the teaching that
you hit the nail on the head. I have to tell one quick story again. I do kind of sometimes monopolize these things, but when I went to Brown, and I was a pretty good student. I was kind of like the all-around athlete guy and a good student. I was going to pre-medical studies, and I had to take 2 semesters of calculus because that was a requirement for medical school in those days. And I had taken calculus in high school, and it was literally like a foreign language. I was really lost. I couldn't understand even why. What does anybody study this? What is this calculus? And when I went to college that first semester, I was really lucky. One of the people who was in graduate school in applied mathematics at Brown was from my hometown. And he kind of took me under his wing. And, I used to go and meet with him once in a while, and I would tell him, I'm struggling a little bit in this calculus. And he was a phenomenal teacher. He was known even among the students, like run to him if you have a problem in whatever area of math. And he really turned me on to the beauty of mathematics and how solving problems, and it just changed my whole approach. And it also, down the line, gave me a lot of confidence later on in dealing with any of the sciences or when I had to analyze. So I felt my brain expanding. So shout out to Professor Gary Rosen. I think he's at USC, the head of applied math there, who really changed my life. Okay, my first question. In your experience, why do students sign up for your statistics courses? Is it because like certain majors require it? Or is it even now, I think hopefully a lot of them are learning that a lot of companies now want somebody that's analytical. What's your experience?
Well, just sort of to review, when I left graduate school, I worked for 20 years at a hospital in Boston, Tufts Medical Center.
Oh, wow.
And while I was there, we started a clinical research program. And so most of the students I was teaching were actually doctors who were in fellowships. They were maybe in their early 30s. They had finished their residency, their internship, and they were learning a little bit about research. And so I remember very early on when we started the program, writing some formulas on the board for doing t-tests, which is a very basic kind of thing you do in statistics.
Yeah, we'll get into that, right?
And, they're not really difficult formulas, but the students were objecting even to that. And I looked at them and I said, wait a second, haven't you guys had physics and chemistry and calculus and all this stuff? And they said, well, yeah, but that was a long time ago. And we really don't want to see these formulas. So I learned sort of early on that the key thing is explaining the concept. The formula is good if you need to do the calculation.
Make it real. Yeah.
Make it real. But, so then once I left the hospital, I went to Brown. I started teaching grad students. Now, grad students are obviously in a program because they want to learn statistics. Many of them these days, because statistics and data science is such a hot field, we get a lot of students who are just interested in learning how to analyze data. And so they're very motivated, but they are obviously focused on getting a job.
Right.
I've recently started to teach the undergraduates, and a lot of the students that I teach are in biomedical or they're pre-med. They've got to learn, they may have a requirement to take a course, or they may just be interested in it. And so what I try to do is motivate them by giving them lots of examples of things I've worked on. I mean, I've been in this field for 30 years, so I've done lots and lots of studies, or just tell them about sort of common things in life where these principles might be helpful. Yeah. Even financial things like making predictions of where your stocks are going to go, or of course, now it's an election year, so this fall, I'm going to be using polling a lot to explain. Polling, yeah. Like where, what does a poll mean and how accurate is it?
Oh, polling, yeah. Mm-hmm.
And the other thing is that it's not always the numbers so much, it's the study design. So what are the biases that are involved in the design? So for example, with the polling, a lot of the listeners may be aware of the fact that polls are often inaccurate because the sample that they're taking is too small, but it's more likely because the sample they're taking is not an accurate representation of the people who are voting. And so that's a problem, whether you're talking about politics or medicine or engineering.
Right. It applies across so many fields. Absolutely.
Right. If you're not studying what you should be studying, you're not going to get the right answer.
Right. It's funny. I was just reading this book because I really went down the rabbit hole, which we're going to get into later about some of the new approaches. But this book by Tom Chivers called "Everything is Predictable." It's kind of interesting. He became a real huge Bayesian, which we'll talk about later on. But just to go back to what you said earlier, it's so funny. Somebody had advised him. I think it was even a quote from Stephen Hawking. He goes, "Every time you put a formula into your book, you lose about half your readers." Right. So, but what I found. I was going to use this line later, but I have to use it now. When my friend who was at Brown, I was watching him do equations, and then he'd say, "Hey, look, it's your turn. You got to dive in there, get your hands dirty." And he said, "Just remember what one of our math teachers back from Long Beach High School told him." He goes, "Math is not a spectator sport. It's like sex. There's no fun unless you participate." So that was his get in there and work on some problems. Okay. One other thing I want to just make a note to the listeners, because again, I want them to appreciate this, because again, you hear so many findings, especially the headline grabbing ones, and that startle you. But science is really based on what makes it science is the scientific method, where you have accuracy, hopefully, of data and reproducibility. Anecdotal reports are nice, but they aren't really proof that something there's that relationship. We know correlation does not mean causation. So what I want to just mention just briefly to the listeners is that basically in the scientific method, researchers are making an observation. So like say, for example, drinking 2 glasses of alcohol a day is good for your heart. Okay. Then they're formulating a hypothesis that you think can be proven. Basically, let's say alcohol drinkers, people who drink 2 glasses of alcohol a day have less heart disease than non-drinkers. Just using this example. Then again, researchers, I'm sure, want to test the hypothesis by a study. So where they have like 2 cohorts or groups, so let's say drinkers versus non-drinkers, and then they follow, I'm sure, like specific cardiac tests over time. And then obviously the statistical analysis comes in by analyzing the data, as you mentioned, looking at the sample size and other things. And then they draw a conclusion from it. So, Professor Schmid, what I want to ask you is, and again, it was interesting, you worked for 20 years, you said at Tufts. So if a team of doctors came to you and said, we think there's something here that we want to analyze, would you help them design the study before they even, obviously started enrolling patients and the medical tests they were going to do? Or did you come in later once they had a lot of data and they said, look, Professor Schmid, how do we analyze this? How do we know if this, came in?
So I get sort of both types of requests. So a lot of times, for example, a resident may have to do a research study, or maybe a younger doctor is trying to get a publication. And so they might have collected some data, oftentimes, in their spare time in the evening.
Right.
They might put it on a spreadsheet and they might come to me. They might try some simple analyses themselves and then they'll come to me. Sometimes It's after they've submitted a paper to a journal and it got rejected or something. And so, we usually say to people like that, well, we'll do the best we can, but oftentimes there are problems with the design or with the way the data are collected. There are too many missing data, or you didn't sample quite the right type of person. And so we can't necessarily fix everything up for you. A lot of modern statistics is trying to deal with observational data that has problems and trying to make it like a randomized study. The sort of the buzzword is causal inference. So you're trying to figure out what the actual cause is rather than just associations. Other times they actually do come to me. They might be writing a research proposal for a grant. And so they have an actual protocol that they're developing. And so I would sort of help them from the beginning. So obviously that is going to work a little bit better in the sense that we can try to deal with all those issues that might crop up later, early on in the process, by making sure that they're collecting the right data in the right way. As you probably know, a big problem in studies is where people make unfounded claims about their hypotheses. Either they think the effect is going to be much bigger than it is, like I've got the wonder drug and it's going to cure everybody, and it only turns out to cure 10% of the people. Or the other issue that often arises is they think they're going to be able to recruit a lot more people than they are to their study. And so this is something that's really interesting. Many years ago, I worked on a trial for chronic Lyme disease. We were working with the NIH, and they were interested in studying whether long-term antibiotics helped at all for people with chronic Lyme disease.
There was a huge controversy on that, right?
Right. And so we were asked by NIH, or we submitted a grant and they funded us to look at that question. And there were 2 separate studies. One was for people who had a positive serology. In other words, they had a Western blot, which is positive. Right. The other was for people who had a negative serology, but they could have a documented clinical evidence of Lyme disease, which was usually a big rash on your back or something, right? Erythema migrans. The problem was we had lots and lots of people, thousands of people interested in being in this study. But when we tried to recruit them, they didn't satisfy the inclusion criteria of the study because they either didn't have a positive serology or they didn't have positive evidence. They would say, well, yeah, I had a rash on my back. But the problem was the doctor had never seen it. It wasn't documented in the medical record.
Right. Good point.
Mm-hmm. We couldn't enroll them. And so the question then becomes, we ended up enrolling about 100 people, and the study actually ended prematurely to some extent because we had a data safety monitoring board, which told us that, it was enrolling so slowly that they wanted to make sure that people were not getting harmed because we weren't finding any evidence of an effect. And so when we actually published it, it was published in the New England Journal about 20 years ago. We basically said there's no evidence of an effect here. But one of the criticisms of the study was, well, you had such a small sample size that.
Well, what do you consider a reasonable? I know, again, the little statistics I know, there's something called like the central limit theorem, like where you have to have at least 30 people, but that still is a small size. What
Yeah.
in your, like 100 people, 1,000,
Well,
in your all these years of experience, again, I'm going to throw this in once in a while, and I know I'm putting you on the spot, and we can't teach a whole statistics course here on this podcast, but like if you were to hear possibly an outlandish results, like I said, like coffee causes pancreatic cancer or whatever, what's one of the first things you would glance at? You look at the sample size?
Well, the sample size is one thing, but I think probably more important for those kinds of studies, which are more epidemiological, is to see what population they actually studied. Mm-hmm. So, for example, a lot of those problems with those, let's say, nutritionally related claims are that the people they've studied are not representative of the general population.
Right.
So there was a study that came out last year about red wine and cancer, or red wine and heart disease. I don't know, it might have been both. And the investigators looked at the data and looked at a lot of the previous studies, which, as you probably know, are very all over the map. I
was about to say, right. 1 year, when you said to me the study that came out, 1 year it's wine protects heart disease. The next year wine can cause, breast cancer or something. It just bounces back and forth.
Right. Another example is the famous estrogen studies, right? Where they originally told women that if you took estrogen, you would prevent cancer and heart disease. And then later on, they came out and said, no, actually, you shouldn't be doing that because it's going to promote.
This drives people crazy.
Exactly. And so the problem is that in a lot of these studies, the hypothesis wasn't necessarily stated correctly. So, with the estrogen studies, there were a lot of observational studies that found an association between, people who took estrogen and reduced risks of heart disease. But then they did a trial to actually test it out, and they didn't find that. They found an increased risk. And part of the reason was because the conclusions are often such that it really depends on the circumstances of your life. So, in that case, it was important whether women had gone through menopause or not. Right. And whether they were taking supplementary estrogens or you were just looking at estrogen concentrations.
Right.
And I don't recall all the details, but those kinds of things, those kinds of details are usually worked out in carefully designed studies. Whereas beforehand. Right. Whereas in observational studies, you're often just using whatever data are available, which
again, I had some extra training in statistics. It's interesting in my fellowship because one of the doctors that would trained us was actually, he was I don't know, what do you call it, a reader for the New England Journal. Like he used to review articles, and he really had a lot of statistics and mathematical background. And one of the things I was looking back at some notes when I took his like little course was that there's a big difference between, as you're saying, observational studies versus experimental studies, where observational has a lot of negatives about them.
Well, there's two issues with observational studies. The first one is that oftentimes you're just using the data that are available.
Right.
And that may not be the right data to answer the question. The second is that a lot of those data are not very carefully collected, meaning that, they might be in an electronic health record, but there's no like quality control on it, or they're self-reports and, people have recall biases. You ask somebody what they ate, how much wine do you drink? And this was one of the things that comes up in the wine studies is people don't recall what they've drunk. Right. So in a carefully controlled study where you're actually asking people to, measure it, or you might even have an instrument which shows how much wine they've drunk, or you give them carefully aliquoted quantities to use every day, you can really measure that very precisely. It's like any problem where measurement is poor, right? If you ask, if you ask a good construction worker to measure something, they're probably going to do a pretty good job because they're an expert at that. If you ask me to go out and like measure like somebody asks me how wide is your fence post? I'm not an expert in that. I might be off by a couple of inches, and if that's important, then that's going to be something that you know um, is a problem. So observational studies kind of have two issues. They're not well designed, and the data are often not very well collected. And
So if you saw that in a paper that came out with some kind of big time controversial thing, you would give less credibility to that.
I would give less credibility to it. Another point I think that's important to make is that I think particularly now these days with large data, big data, and AI, we kind of have come to the belief that, well, if there's enough data there, if there are enough observations, and if there's some machine that's an expert machine doing the analysis, that somehow the answer is right. And first of all, big data are only as good as the design on which they're based. I can, there's a very famous example that you've probably heard of back in the 1936 presidential election, which is Franklin Roosevelt and I think it was Alf Landon. They did a telephone poll in the United States, and they called people up and asked them who they were voting for. And it turned out that the Landon, the Republican, was way ahead in the poll. And so they predicted that the Republicans were going to defeat Roosevelt. That was his second term. Turned out, of course, that Roosevelt won in a landslide. And what happened there is basically that the poll was very poor. And it's poor because people who have telephones are, in those days, were wealthy, and those were the Republicans. So the poll was badly based, right? Because it's basically just sampling a subsample of the population that's not at all representative. And this happens a lot with big data, where you might collect a lot of observations, but if they're not the right observations, you're not going to get the right answer. Likewise, with the machines, if the machines aren't programmed correctly with the right algorithms, they won't get the right answer either.
Yeah. Let me ask you this also too. It was a title of a chapter in a book I was reading. It's actually a great book. It's called Super Thinking by Gabriel Weinberg. Yeah, where he talks a lot about analyzing data. And so one of the subtitles is Lies, Damn Lies, and Statistics. Now, is it true in your experience that results can be slanted to make an outcome more likely? And just as a sort of follow-up to that, were you ever involved where, let's say something came out bad, like, it came out, 2 glasses of wine is associated with breast cancer or prostate cancer or something, and then the alcohol, lobby came and said, you know what, we're going to fund a big study to show that's not the case. And they go to some doctors at Boston, the Mass General or something, and said, okay, let's gear up a multi-year study to really show that, alcohol has no effect on cancer. Have you found that to come into play in your experience?
Well, not really in my personal experience. I mean, I do know those kinds of things probably do happen. I mean, there are a lot of studies where companies are going to try to promote their own product. In terms of that quote, which I think it was originally due to Disraeli or somebody back in the 19th century. There are a lot of different ways of analyzing data, and particularly when you have small sample sizes, the answer can be different depending on which analysis you use. And so there are people who will use the analysis that gives them the answer they want to find. This is particularly problematic in the literature because, as you probably know well, a study is typically published if it's significant, and we typically use a p-value of 0.05 as the significance level. That's just tradition. And so if you do your analysis one way and you get a p of 0.04, that says that the result that you're looking for is true. And if the p is 0.06, then you can't claim that result. And so right. And which analysis are most people going to use? They're going to use the one that, and it's not just even something as simple as that. It might be that one analysis adjusts for certain variables, and that adjusted analysis gives you the answer you want. So this is why a protocol is really, really important. And when you publish a clinical trial these days, you have to register it, have it registered at clinicaltrials.gov, which is a website that's maintained for protocols for clinical trials. And if you want to publish in the New England Journal, you have to send them your protocol, because the idea is you should really only be analyzing something that you plan to analyze. You shouldn't be making up your analyses after you've looked at the data. In other words,
well, let me ask you this too. You probably heard about this too. I think the more recent was at Columbia Presbyterian, which is a great hospital. I did a lot of training there. The medical center. But like one of the again, one of the researchers, professors there, like a slew of his studies were being, I don't know what the right word is, reevaluated or being retracted from journals. Like, and again, it seems like there's like some people out there who are like sort of watchdog groups that like are looking for this. What is going on there? I mean, let's say you get a prestigious person. Obviously, he got the article published in a prestigious journal, and then somebody's going back and saying, this doesn't really cut the mustard. What is going on there?
Well, as in most fields, there are unscrupulous people who are just trying to get ahead by cheating. But okay. That's true everywhere, and so that's true in the medical profession as well. And so sometimes what happens is that it could be something that's not really meant incorrectly, but there's a lot of staff and students and trainees on these things, and those people might make a mistake that somebody misses. But in a lot of these cases, I think these are images where they've been doctored. So they might do an image of a body system, like an MRI or a CT scan or something, and they doctor the image somehow. And so what these investigators have done is they can use AI to basically compare images. And they will find, for example, that the image in one paper is exactly the same as the image in another paper, or it's reversed or something like that. So it's very clear that it's not a new image. It's been used over again. And so in some cases, this is how they can discover that something not quite kosher has occurred.
Mm-hmm. And it's actually more difficult, obviously, being the detective, to find these errors, because these people obviously who are even who are finding these problems haven't done the studies themselves. They don't know what the researchers did with the actual experiment that showed the results, all down the line.
There's another issue too, which is that, you would say, well, this should be caught in peer review, right? So peer review is the system that we have where if you submit a paper to a journal, the journal is supposed to get several experts to look at that paper and verify the results and make sure that the paper's well written and all that. And so you'd think, well, shouldn't the experts be able to catch that? But two things happen there. One is, of course, most of those reviewers are volunteers. And so they can only spend a certain amount of time on it, and they may not catch it. The second is, a lot of times it's really, really hard from the published material to figure out inconsistencies like that. The reason that some of the detectives can figure it out is because they have software which can troll through the internet and find all the other papers that this person has published and compare things and say, well, wait a second, this picture in your paper in 2010 is the exact same picture that you published in 2017, but these are different studies.
Wow.
As a reviewer, I don't have the time to go back.
Right.
And look,
I get it. It. Yeah. And it's funny. I just always wondered too, the reviewers, again, let's say a cardiac study, they're going to some of the top cardiologists in the country, but they're not statisticians either. I mean, they understand, what an angiogram or an echocardiogram should look like, and the findings. But when you start to do the statistical magic, this is statistically significant, this one's not. I really don't know. Again, like a lot of your experience with doctors, this is not their, they don't like formulas. And they're not familiar with so many of the, the different kind of analysis and all the parameters, et cetera. Right.
Right. That's true. I mean, one of the things we try to do at Tufts was to train the doctors to be able to do some statistics. That makes a huge difference. I mean, I've always told my statistics students, it's always better to work with a doctor who knows statistics, but you better know some biology and some medicine too, because otherwise you're not going to be able to help them. And likewise,
the collaboration.
The doctors need to know some statistics. But I think in a lot of these cases, the top journals will have a statistical reviewer. So, for example, I've been a paid reviewer for the American Journal of Kidney Diseases for almost 20 years. And so they will send me papers that have statistics in them to make sure that the methods are done correctly. And I review maybe, I don't know, 20 or 30 papers a year for them. So, that's the National Kidney Foundation. And so they pay their reviewers. And so that's something that I put a priority on, right? To make sure.
And if they pay you and you're reviewing it and you look at it and now these are papers that have been published already?
No, these are papers that have been submitted for publication.
Submitted. Okay. Yeah. So if you look at one of those papers and they say, oh, wow, this drug really helps, slow the progress of kidney disease. But you look at it and you say, oh, I got a big problem with the way they analyze the data. Is that something that you give them the feedback on and it should squash that, or have them go back and read, provide more data?
Yeah. So, I'm looking at the methods and I'm also looking at their results. And, there are quite a few papers that have been submitted to the journal that I've recommended for rejection. And, usually when I recommend for rejection, it's not because the paper has some problems with it, but because it fundamentally can't be resolved. In other words, they've got the wrong population, or, if they've done the wrong analysis, that can be fixed. And a lot of times I've suggested you don't have a statistician on your paper, get one who knows how to do the right analysis. I actually review a lot of meta-analyses because that's I
want to get to that in a minute. Yeah,
that's something I've done a lot of.
I want the listeners to understand what we're talking about, but yes, we're going to get to that in a moment.
So meta-analysis is the practice of putting together studies to figure out what they mean in total. And so one of the issues there is, do you have all the studies that have been done in the area? And so a lot of times when I review papers, for example, in meta-analysis, I might reject it because I'll say, hey, look, you're missing half the papers here. Or even another issue might be that they found a lot of papers, but they've excluded them because those papers, for example, didn't report the right outcomes. But then there's a whole issue of publication bias, which, is something which means that people did not publish a result that wasn't significant either.
Yeah, these are really important things. That's why I want, again, the listeners to get this. Like, when because they're getting second, third hand. The New York Times, whatever reports, Nature or JAMA, found this. They don't hear about the negative studies because they never even get published.
That's right. Right. And
the other thing, which I want to just make it look clear for the listeners, because we are getting a little bit into statistical jargon, like meta-analysis. From the best of my understanding, I would see it in my journals, and typically it would tend to indicate a more prestigious, credible finding, because supposedly they were taking like 30 studies. Is that correct? 30 studies that were already done on this area. Mm-hmm. And just kind of pooled and analyzed the data more to say, versus just taking this one study here or this one study in this journal. It's like saying, let's look at all 30 journals that published about, maybe the connection between, cholesterol and heart disease. And that's supposed to, I assume, instead of having, to get, again, more credibility to those findings.
Right. So meta-analysis has a couple of advantages. One is that because, in essence, you're getting bigger sample sizes because you're looking at more studies. Let's say you had two studies, which, again, to go back to the p-value analogy, both had p-values of 0.06. So they were trending in the right direction, but you couldn't quite. Well, if you had 15 studies like that were all in the same direction, but they weren't quite big enough to get a statistically significant result, then when you did the meta-analysis, that consistency would lead you to believe that it really was a true result. It's just that none of the studies was really big enough. So that's one advantage of meta-analysis, is it can give you some more precision. The second advantage is that, as you know, many times when studies are done in an area, they come up with different answers. So one study might be significant, one study is not significant. We've talked about the idea of the food you eat, and coffee and pancreatic cancer or whatever, right? Some studies significant, some studies not. So another advantage of meta-analysis is you can actually, because you have all the studies in front of you, you can look at them all and say, okay, well, why were these ones significant and why were these ones not significant? And you might find, for example, oh, well, the studies that were significant were all looking at people who drank, I don't know, highly caffeinated coffee or something like that, right? Whereas the studies, the other ones were, or Colombian coffee versus, Ethiopian coffee or something like that, or men versus women, right? So it can look at what we call heterogeneity. In other words, the fact that the populations or the treatments or the characteristics different. And so that's leading to those different answers.
One of the things you mentioned, I just want to clarify for the listeners too, when you kept on saying about p-values, it's what we call a probability value, right? And I remember, as I said, in college, I took just calculus, but in medical school, they did do a semester on statistics, which I was glad they did. Didn't really enjoy it that much at the time. That teacher wasn't so great. But but what I do remember, because it was sort of mind-boggling, confusing, was this thing called the student t-test. And basically, what you're alluding to is, and I'm going to say it, but hopefully you'll correct me if I'm not saying it right, is that essentially to see if a study is what we call a positive study, meaning, that the data is showing something that's proven to be true, you have to reject the null hypothesis, right? And just as a translation, tell me if I'm saying this correctly, so that if a study has a p-value, a probability value of 0.05 or less, that means that there's less than a 5% chance that it wasn't true. So on the flip side, there's a 95% chance that it is true.
Yeah, I mean, this is
it's like this backwards thinking,
Yeah. This is part of the reason that I really like Bayesian inference better.
We're going to get to that. Don't give away the story yet.
To understand. But technically, what a p-value? Okay, so let's say you've developed a new drug,
right,
that you think is going to make people's health better, right? So the null hypothesis is that the drug isn't any better than the standard.
Right. So you're trying to be negative. You're trying to say, yeah, there's no difference between that and whatever. Yeah.
Right. And your alternative hypothesis that is better. So you're basically assuming before you start that there's no difference, and you want to show that there is a difference. So you do the study, and the idea of the p-value is if there really was no difference, in other words, if the null hypothesis is true, what is the chance that the result you would have seen occurred? So let's say I find a huge difference, that the people on my drug get much better than the people who didn't take my drug. Then the chance of that happening, if there really was no difference, is very, very small. That's the p-value. So if the p-value is small, it means it's very unlikely that there was no difference. Or in other words, it's very likely that there is a difference.
It's just sort of backwards thinking, but
exactly, and that's why it's really, really hard for people to kind of grasp that concept.
It really is. The only thing I can tell you, though, it's interesting because, again, in my limited statistical background, is when I look at a paper, because it's really part of my job. When these things come out, and I read the New England Journal, I read a whole bunch of journals, and honestly, again, it's sort of like my crutch. One of the things when I'm looking at the findings, the conclusions, I say, Dean, you got to go in there and look at the statistics a little bit. So let's see what's going on here. So I'll look at the sample size, and I'll look at the p-value in a lot of these cases. And obviously, I know if it's 0.001, that should be a very strong statement that it's that the alternative hypothesis is true. But okay,
right. So one issue with the p-value is it's a function of two things. One is, well, actually three things, but one is how big a difference you found, right? The bigger the difference you find, the smaller the p-value. The other is it's a function of the sample size. So if I did two studies, one which was really, really big and one which was really, really small, the bigger study is going to be more precisely estimated than the smaller study, just because it's got more data. Therefore, I can find a significant result with a smaller difference with the bigger study than I can with the smaller study. And so therefore, the p-value also reflects how big the study is. So if you find a p-value of 0.001, but you have 1 million people in the study, the real difference might be tiny. And it might even not be that important clinically. But it's just that you have so many people in the study that tiny, tiny difference is significant.
That's interesting. So
right?
these are all like these key points. And I feel bad. I don't want to get our listeners lost in this, but I can't emphasize enough throughout this how important this is because, again, so many decisions about our health and medications and procedures rely on this analysis. And, so, all right, let's move on to what really got me seeking out a person with your expertise. As I said, I just happened to be, I don't know why I got on the bandwagon. I was reading this book, I think, which you're familiar with, The Theory That Would Not Die, which was written by Sharon Burst McGrain, which is about basically what they call Bayes' rule. And then I kind of saw, I think in one of might have been the Wall Street Journal, this book recently came out by Tom Chivers, Everything is Predictable, and has and they call it this Bayesian statistics. Now, I didn't know because I wasn't involved, so focused on this, but apparently this was a very controversial, almost like, buried type of statistical analysis. Thomas Bayes, I believe, was a minister or something.
He's a clergyman,
Clergyman in England. And in his spare time, between doing his stuff, he was playing around with math and statistics. But apparently, and even after his death, his approach to statistics was like, persona non grata, like do not talk about, this kind of thing, because the real movement, I guess there was this guy Fisher and the t-test, and I think what they called them the frequentists, that were sort of, let's just look at the data and see, is it right? Is it wrong? Whereas, and I'm summarizing, but we'll get more of your expertise, where Bayes said, look, we have to know what our prior information is, what our base rate about something is, and that makes it easier to predict about, whether or not something is statistically significant. And the other thing, which I just would caught my eye about these particular books, was that apparently this type of probability analysis is used in a lot of areas. When I believe something I think it was in World War II, they were trying to find the German submarines. They were trying to plot and figure out where they most likely were going to be to attack them, and they were using this Bayesian inferences. Right. They pulled out the mathematicians. All of a sudden, no, don't send them to the front line. We need them to analyze the data. So, tell us a little bit. Some of you, and I saw a couple of articles when I went on Google that you had written. And we talked about this before, but I think one was with an emergency room physician out in California, I think you were with. But
Chris Gill actually was a fellow at Tufts who I taught there, and then he went over to BU, and I had taught a little course on Bayes statistics, and he was really interested in it. And his paper was called "Why Clinicians Are Natural Bayesians." And so the basic idea with Bayesian statistics is, so there is a whole history behind it. And in fact, in the 19th century, Bayes statistics was probably used more than any other kind of statistics. It was then called inverse probability, because Bayes' rule is a way of, if you want to calculate the probability of something, given that something else has happened, you can flip it around and calculate it in the opposite direction. And that's just a mathematical formula. That there's nothing controversial about that. Mm-hmm. And so people had used this, but basically, Fisher, who invented a lot of sort of modern statistics, he did not like this approach, and he was highly influential. And so for a long time, it sort of got out of favor. It's now used quite a bit, and in fact, modern statistics is sort of a mix of the two. And there are a lot of problems where you really can't solve it with frequentist statistics. You have to use Bayesian statistics. But let me just give a step back and just sort of explain. Yeah. So there's two parts of a Bayesian problem. The first is, as you said, the prior distribution. What the prior is it. So let me see if I can give an example. Let's say you were trying to estimate the probability. So I'm a big Celtics fan, so I'm watching the basketball games now. Let's say you're trying to pick the probability that that the Celtics were going to win the game tonight against the Dallas Mavericks, right? So you could use some data to calculate that probability. Now, as the game goes on, listeners may be aware that the betting odds change. And nowadays that the professional sports are so into betting, they will often show you this in the middle of the telecast. So you can think of the betting odds right now before the game starts as the prior probability. So the Vegas odds makers are using lots of information to figure out the odds that one team is going to win the game compared to the other team, and they set their line that way. Then as the game starts, you start to collect some information on the game.
Right.
And those odds change. Well, that's exactly what Bayesian statistics is. It says you have a prior distribution, you start collecting data, which technically is called the likelihood. You combine them together with this Bayes rule, and you come out with a new distribution, which is the posterior distribution, which is your odds posterior to getting the data. Now, let's say that I've updated my odds after the first quarter of the game. And before the game, let's say Dallas was favored by 3 points.
Right.
But in the first quarter, Boston goes out to a 20-point lead.
Right.
So now the odds switch. Now maybe Boston's favored by 5 points. I could now place a bet at the end of the first quarter, giving 5 points on Boston. And I can think of that now as my new prior. It was posterior to the first quarter, but it's prior to the second quarter.
So it would seem very important, as long as as they say, the base rate of the prior was accurate. Because if that wasn't accurate, I mean, obviously in that case, you know what the first quarter results are. Or the other thing I was just thinking about as you were talking was like, let's say Dallas was favored, but after the first quarter, the star player on Dallas got injured and he couldn't play the rest of the game.
Right.
So.
Right. So all of that goes into the prior, and in fact, one of the big complaints about the Bayesian formulation is that a lot of people who don't like Bayesian inference say that, well, the prior is very difficult to measure, and a scientific result should not be subjective in the sense that it shouldn't depend on information that you can't scientifically collect. But of course, the prior is often based on information. It's just that it's not necessarily information that's coming from the current study. To give you another example, if I work for a drug company, a pharmaceutical company, and I make a product and I submit it to the FDA for regulation, and I do 2 clinical trials, let's say, that support my product. Let's say those clinical trials are marginally significant. So they favor my product, but not by a lot. So I went into this exercise having done all my animal studies, all my clinical development. I wouldn't have invested a lot of money in this product unless I thought it was going to work. I did 2 studies, it worked. I'm pretty convinced that this drug is effective. The FDA should let me sell it. The FDA, though, is a regulatory body. They're going to go in with a very kind of not a negative attitude, but they're going to be pessimistic. And they might say, well, you've got to really convince us that this thing works because we're concerned that it might harm people, right?
Right.
So they might look at those 2 marginal studies and say, that's not enough evidence. You haven't convinced us. Now, 2 bodies have looked at the exact same set of data and they've come up with different conclusions. Why? Because they had different priors.
Right.
That's where the Bayesian inference comes in, is that the frequentist cannot distinguish between those 2 decisions because to them, you did the analysis. It could be a meta-analysis of the 2 studies too. And yeah, the p-value was 0.04 or whatever it was. It's significant. Why did they come up with a different decision? It's because they had different priors. And so the idea of the Bayesian is you quantify the prior so that the posterior is also a statistical answer.
Yeah.
But 2 people could have different answers even with the same quote unquote data because they have different priors.
Yeah. The thing to me about the priors is 2 things. Science is usually built upon prior work. I mean, we can't start from scratch all the time. There are certain things that, we know, for example, DNA, how it affects RNA, just in those things. And we sort of need that. I think what's interesting, though, is where, but that also, there's a slight bias because you're assuming that whole thing's right. And the reason I'm bringing it up is funny. I just got a book on RNA, and it's like, but years later, people realize, oh my God, RNA in some ways can be independent of DNA. So it's like sometimes a finding or observation or something can really throw a wrench in what was considered an established fact.
Yeah, and so again, the way I think of Bayesian inference is it's an iterative process. So my current state of knowledge becomes my prior for my next study.
Right.
Now, if the next study is contrary to my prior knowledge, so let's go back to the estrogen studies. So before those clinical trials were done, the prior was very positive that estrogen could reduce your risk of heart disease. Then they did those studies and they were negative. So now your posterior should have changed, right? It should have gone in the other direction.
Right.
It doesn't, and it's a probability. So it's not like the final answer because science usually doesn't have a final answer. We're always learning something, right? Yeah. So we're always updating our knowledge. So when Chris wrote that paper on why clinicians are natural Bayesians, his point was really in the idea of the differential diagnosis.
Yeah.
Which is that, he is an infectious disease doctor. So he said, all right, let's say a patient comes into me and they have certain symptoms and they ask, I'm trying to figure out what they have. Okay, so I might not be quite sure and I might run some tests.
Right.
Now, if the patient tells me they just returned from Central Africa and I know there's an Ebola outbreak there, I'm going to have a very different diagnosis than if I didn't know that, right? That's the prior information that I'm going to
It's so important. And as clinicians, we constantly have to build on that on the fly. It's not like we have like 3 months to kind of look over data. We're constantly making these judgments. It used to be called also heuristics in a way, like sort of the gut feelings, and then a lot of things have kind of gone against that. Like, let's look at data. So, actually, it brings me to, as we're kind of getting near the end, I wanted to ask you about AI. Mm-hmm. And it's kind of, I hadn't thought about this until I was getting ready for this podcast, but, obviously AI is the whole craze now and data. But, I was thinking that it could be obviously extremely important. I mean, I think AI is going to be very important in medicine in image analysis, because I think, again, it'll be, I think the term, I hate the word artificial intelligence. I like I like the word assisted intelligence, because that's the way I look at it. And if it's like sort of cutting down some of the drudgery work, obviously a radiologist comparing a film from 4 months ago to now, if a machine could do that with better accuracy and the radiologist is just sort of double checking it. But what do you see the role of AI, like, for example, in maybe medical statistics? Do you see where you get even these meta-analysis, they can feed this data into an AI and it'll be able to, be that watchdog to see if these studies are not legitimate? I mean, is that on the horizon?
Yeah, I mean, I think AI has a lot of potential. It also has a lot of potential risk to it. So, a good example are all these instances now where we found that AI is very good at recognizing certain faces, but not other faces. Okay. Like, it recognizes white faces very well, but not black faces. Right. People of color, and so that leads to discrimination and all kinds of things. I'll give you an example from my own work. So many years ago, maybe 15 years ago, we developed a predictive model for GFR, glomerular filtration rate,
kidney function,
which is used a lot. And it was based on your age, your sex, your creatinine, and your race. And what we found when we analyzed the data was that the GFR was higher if you were Black than if you were not Black. And so we put that correction into the model.
Right.
And so what it meant was that if you were, let's say you're so generally, if your GFR goes below 60, it's recommended that you might want to start treatment for kidney disease.
Kidney disease, right.
So let's say you're a Black person and your GFR is 58, but now I use this model And it bumps up that predicted GFR to 62 because you're black, whereas the white person is 58.
Right.
So the black person is not going to get treated. The white person will get treated because the black person is above the cutoff of 60, and the white person.
But can you put that into now with that knowledge and information, you put that into the AI thing. Maybe when I get a lab back from Quest or LabCorp, one of those places, that should catch that and hopefully correct.
Well, no, what it's going to do is that the AI system is going to say that the GFR for the black person is 62, but for the white person it's 58, given the same age, sex, and creatinine. So in other words, the you looking at it would say, oh, your GFR 62, you're fine, you don't need anything. Whereas the other person who's got the GFR 58, you might want to put them on some medications. In other words, the black person would be treated even though they have the same age and sex and creatinine level. Just because of their race, they wouldn't be treated. Now go to the lower end, right? So dialysis, let's say your GFR falls below 15. Now the black person is not going to get dialyzed or might not get a transplant. And so this is one of the issues, is that if you just look at the data, the people of color are not getting treated as much because the algorithm is saying that their actual levels are higher than the white people.
And that's not fixable? That sounds like so easy.
Well, it's fixable. It's fixable, but if you believe the data, and if the data are telling you that a black person of the same age, sex, and creatinine level actually has measured GFR, because remember, we're developing these models on people who have measured GFR. So what the model is saying is that if you measure the GFR on the black person, it's going to be higher than on the white person, right? Okay. So this became a big issue. It was in the New York Times a few years ago, and they fixed it. They got rid of the race equation. But then what it will say is that now the white people are not going to get that benefit. And so some people have argued, well, now there's a bunch of white people who are not getting transplanted, who should have gotten transplanted or whatever. So this is the issue with AI, is that it's only as good as the models it's based on.
Got it. Yeah, that makes sense. Right. The humans who programmed it with the information.
Right.
Yeah.
And so if you don't have the right information, or you were talking earlier about people who kind of fix up the data, you can obviously choose whatever you want to run your models on. And so, even like automobile systems like driverless cars, right? So they work great, except maybe there's a situation that they haven't programmed. And so it leads to an accident. So that's the problem with AI, is that it's only as good as the people who are programming it.
Yeah. Professor Schmid, one last thing too I wanted to ask you about. When I look at a paper, when it comes, in the in New England Journal, whatever too, I'm reading through the abstract, and how it was studied, I'm looking at the conclusion. And then if I'm really like spending a little more time, I'm looking at the charts, I'm looking at graphs. And some graphs are like horrendous to follow. I tend to like what's called like bar graphs or histograms. To me, they're just easier to see. Do you find most of those things fairly reliable, and are they good in a sense of telling the story of what the data is showing? Because for some people, again, to get into the weeds of figuring out, is this positive, negative? A good bar graph, histogram, or something, versus those crazy plots, which I hate. Where the lines going every which way.
Well, so graphics is really, really important, because this is the way most people present a lot of information. A good graphic is really worth a lot. And it's very easy to mislead on graphics. Everybody's probably familiar with the Dow Jones stock chart, where it shows that, the straight line down saying the stocks are doing really horrible today. And they've gone from 35,270 to 35,260, like it's a 0.001%. But yeah, you can make it look like a perfectly, straight line. So bar graphs are good. A lot of times I find, though, that people can put more information into a graph than they want to. A great example is the pie chart. The pie chart, for most graphical experts, is a really bad use of a chart, because it's got a lot of color and a lot of ink with very little information. And in fact, if you're just comparing slices of pie, it's often really hard to tell which is bigger. You need the numbers there. You're better off just giving people the numbers.
Yeah, I agree.
So, but there are a lot of tables where people just put too much information into it, and it's just really, really hard.
Yeah.
Yeah.
You know, talking about your Celtics, I was also a longtime Knicks fan. The one statistical idea that I've always kept in mind, and it's served me well in life, I think, and even in the stock market, is the statistical concept of reversion to the mean. And then you know that too, even with the Celtics, they had their Larry Bird, Bill Russell years, whatever, 2 champion years. Then they went through a drought, you know, and my New York Knicks have gone through a drought for about even longer than that. I'm waiting for them to revert to the mean. But I just do feel that statistics is an important way at times to look at medicine, life in general. So anything else you'd like to just pass as we're finishing up that you think the average listener should maybe pay attention to the best that they can?
Well, I mean, one thing you mentioned is regression to the mean, and that's a really important concept for people to know, which is that something might look really, really good or really, really bad, but it could be a short-term phenomenon. And if you don't follow something long enough, you're not going to see the true pattern, right? And so making predictions too early can be a real disadvantage too. You really need to see the whole situation.
Yeah, that's a great point. Because I think, yes, I think it's really a good way to end, because sometimes when you look at a duration of a study, I mean, just to throw it out too, like for good or bad, like the Framingham study, that did the heart study. I mean, that was a pretty intensive, long-term study. I'm sure there were critics about things, but it is considered still to be one of the gold standard studies because they looked at things over such a long period of time.
Right.
So, Professor Schmid, I want to thank you so much for taking the time. I got a little bit smarter today. I hope also most of my listeners have, and appreciate what goes on in trying to make sense of a lot of the medical research that comes out in everyday life.
Well, thanks. It was a lot of fun talking.
All right, good. I'm glad you enjoyed it. It was terrific.